Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp, Lecture 12. We're going to be talking about non-parametric statistics. Okay, in this video we're going to be talking about non-parametric tests, which include the sign test, which was useful for paired tests, which is kind of related to McNemar's test, the signed rank test, which is also for paired data. We'll talk about Monte Carlo versions of that test. We'll talk about independent group test, and then from that the Mann-Whitney test and Monte Carlo versions of that, and then their relationship to permutation test, which are very closely related. Okay, so very briefly, we're going to be talking about here about so-called non-parametric tests, but very kind of classical non-parametric tests, and these are often called distribution-free. That, of course, doesn't mean that they're assumption-free. They involve assumptions, for example, sampling assumptions such as IID-ness. But they require fewer assumptions than parametric methods. They have a tendency to focus a little bit more on testing rather than estimation, which maybe is a problem, but there are estimation techniques that follow, though they also tend not to be very sensitive to outlying observations. And they're especially useful for data like ranks, if the data actually come in the form of ranks, because they often involve transforming data to ranks. They're not uniformly wonderful because they do throw out some information, which is their problem. And because of that, they may wind up being less powerful than their parametric counterparts when the parametric assumptions are true, of course. And then, for larger sample sizes, they become about as efficient as their parametric counterparts, so they are pretty good tests. So here's some data from this wonderful book from Rice called Mathematical Statistics and Data Analysis. I highly recommend this book. I use the second edition. I don't know if that's what they're still on. At any rate, this data concerned 25 fish. They were taking mercury levels from the fish in parts per million. And they had them at 2 locations on each fish. So fish 1, they had a measurement of 0.32 and 0.39 and so on. Okay? And then just for reference here, I've added the difference between those 2 measurements, subtracting the p from the SR one each time. And then I'll show the ranking and the signed ranks. I'll explain those in a minute. But this is the data we're going to use as motivating data. Here we want to test whether the mercury levels taken at location P differ from those of location SR. Where here, we're taking 2 measurements per fish, trying to control for the fish-to-fish variability by taking both measurements on each fish, having each fish serve as its own control. But we're going to be talking about non-parametric tests. So what we're interested in or concerned about is the validity of the assumptions that go into typical tests, such as normality. Okay, so let's let DI be the difference for each fish. In this case, I'm subtracting P minus SR. And then let's let theta be the population median of the difference of the differences DI. And we want to test whether that median is 0 versus the median being non-zero. Now by the definition of the median, if theta equals 0, only if the probability of a difference being greater than that value, 0, is exactly 0.5, right? That's the definition of a median. Same thing for less than 0. So as a test statistic, why don't we just count the number of times that d is bigger than 0? And if it's excessively large or excessively small, then that's going to dispute the idea that the median is exactly 0. So just as an example, if all the differences were positive, then 0 couldn't be the median, because you wouldn't expect a large sample where every single measurement was larger than the population median. Okay. Anyway, then x here, each difference, if we're assuming the fish pairs are IID, then each difference is a coin flip with a 50% chance of being above the median or a 50% chance of being below the median. So the number of times it's larger than 0 is binomial, n in p, and in this case p is 0.5. So our sign test just tests whether p is 0.5 using this data x, and you can do an exact binomial test like we've talked about before. Okay, so let's go back to our example. So theta is the median difference of p minus SR. Our null hypothesis is that theta equals 0 versus the alternative that it's different from 0. The number of instances where the difference is bigger than 0, in this case, go back to the table, it works out to be 15 out of 25 fish. And the binomial test then is the question of whether 15 is large, 15 positive instances out of 25 is large. Now our expected number out of 25 is 12.5. So, 15, we don't know whether 15 is excessively large. Well, in this case, it turns out that no, 15 is not excessively large. It has a 0.42% chance of happening under the null hypothesis for a two-sided test in this case. And again, we could have used a large sample test. I don't know why, because we can do an exact test in this case, but we could have used a large sample test, and that's prop.test, and you get a chi-squared statistic then of 0.64, a p-value that's quite similar, 0.42. So at any rate, the idea is that this is simply just testing. If you're going to assume that levels of one are higher than the other, then you're just going to count the number of pairs from the matched pairs where it's higher, and is that excessively large relative to a coin flip for each pair. So that's the sign test. Now you might be wondering, what's wrong with this? So let's discuss some potential problems with this test. Because it doesn't use very many assumptions, right? We aren't using very many assumptions. We're using that the fish pairs are IID, and that's about it, right? That's the only assumption that we're using. But let's talk about what's maybe some of the problems. Okay, so the biggest problem is, of course, that the magnitude of the differences is discarded. So it's potentially not as powerful as you'd hope, right? It'd be different if maybe if you only got half of them as being positive, but all the ones that were positive were much larger differences, and all the ones that were negative were really small differences, then that would be different than if they were kind of spread equally between above and below 0. So I would say that. But then the other thing I would mention is there's nothing specific about 0. You could have tested any median, theta equal to theta naught, by calculating the number of times the difference is bigger than any specific value, testing whether the median is bigger than any specific value. What's interesting about that, then, we won't talk about this, but it is kind of interesting, right, that you can do this for any value of theta. So that means you can find the values of theta for which you fail to reject and the values of theta for which you reject. And then, of course, if you can do that, by a grid search or say, something like that, then you can invert that and get a confidence interval for the median. And so this is kind of an interesting way, a very highly non-parametric way to get a confidence interval for the median of a set of data. So Wilcoxon thought about this problem of discarding the magnitude of the differences, and he said, well, why don't we, instead of using just the signs, why don't we also use the ranks of the differences? So using the ranks saves some of the information regarding the magnitude of the differences. We're still testing whether the median is 0 versus the 3 potential alternatives. And we can create a statistic, and I'll say that appropriately normalized, this statistics follows exactly a normal distribution. But if there's no ties, then the exact small sample distribution is known, and then why use the normal distribution? The one benefit of the normal distribution in this case is because the small sample distribution is known, we can evaluate how accurate the normal distribution is in general. So it's different than a standard normal distribution where you don't know the exact small sample, the associated small sample distribution, so you can't tell how well the normal approximation is working. So I would say at least that one aspect of normal approximations in non-parametrics test is a little bit different than normal approximations in general, because we can evaluate we have a much better sense of how well the normal approximation is working. So here's the signed rank procedure. So we take all the paired differences, just like we did before. We take the absolute values of the differences, which is new. Now we haven't done that. And then we rank these absolute values from least to greatest, throwing out the ties, throwing out the zeros, is what I mean. And if there's ties, right, there's a difference between ranks of 0 and ties. If there's ties, in other words, two differences are identical but non-zero, then we use the average rank. We assign the average rank to those. And then after we've done the ranking, we multiply them by the sign of the difference, +1 for a positive difference and -1 for a negative difference. And then we calculate the sum of the positive ranks, and that's the signed rank test. Now, so think about what this is doing. Let's suppose we did have the case where all the big measurements were positive and all the smaller measurements were negative. smaller differences were negative, smaller in absolute value differences, then what you would see is that all the small ranks would have a negative sign and all the large ranks would have a positive sign. So the sign rank statistic would be very different from what you would expect by chance, where the signs are distributed equally among the ranks, versus the sign test by itself, which if roughly equal numbers were above and below 0, then you would get the same, then you could get a statistic that was highly looked a lot like it was from the null. So just to reiterate this point, if the median is large, then W plus should be large. If the median is small, then W plus should be small. And this W plus, it does follow a normal distribution for large samples. For small sample sizes and large sample sizes, but especially for small sample sizes, we can work with an exact distribution under the null hypothesis, and we can you can get critical values from a table, but you can get the critical values in R pretty easily. So it's maybe a bit involved to exactly work with the null distribution. We'll do some of it, of the exact distribution of the statistic. We'll do some of it. But I wanted to at least talk about Monte Carlo, so you could at least see that, okay, so we can pretty easily figure out what the exact distribution is, provided there's no ties. What you could do, so if this procedure is invariant to the distribution being used, you have to simulate. So what you could do is simulate n observations from any distribution that has theta as its 0, theta is 0, its median is 0, and then rank the absolute values of the data, retain the signs, calculate the sign rank statistic, and apply this procedure over and over again, and you'll have just used Monte Carlo to get the exact distribution, especially because we're assuming this distribution is invariant to, we could use any distribution, like for example the normal distribution, the standard normal, and that would give you the exact small sample distribution. But we can actually go further than that. This distribution under the null hypothesis, right, the signs are equally likely to be distributed anywhere among the ranks. So all you have to do is actually take the ranks of the numbers between 1 and n and just randomly allocate the signs, okay? And that's exactly the, flip a coin for each rank value. So take the rank 1, flip a coin with success probability 0.5, take the rank 2, flip a coin, and so on. And then you've just generated this distribution exactly. You haven't had to mess around with a normal distribution or something like that. But I present it this way just to show you conceptually that, well, if this test really doesn't depend on the distribution, then you could pick any distribution and just simulate under a null distribution. But I'm contending that it's even easier than that. All you have to do is take the ranks, i.e. the integers from 1 to n, and flip a coin for each rank, and then you'll have exactly giving a +1 and a -1 for a head or a tail for each rank, and then you'll have exactly calculated the null distribution of the signed rank statistic. So it works out very conveniently. Okay, so I in fact actually say this explicitly on this slide here, where here's a little bit more elegant way to do it. Take the ranks 1 to n, randomly assign the signs as binary with probability 0.5 of being positive and 0.5 being negative, and then calculate the sign rank statistic. At any rate, if you wanted a Monte Carlo p-value, you would just apply this procedure, simulate over and over again, and calculate the percentage of times your test statistic was more extreme, and then that would be the probability of obtaining a test statistic as or more extreme. The average of the number of instances where your simulated test statistic was more extreme than your observed test statistic would be a Monte Carlo approximation to your p-value. And then let me just go through the large sample distribution. I'm not going to derive it. Am I going to derive it? No. It's actually pretty easy to derive, to be honest. If you think about it, right, it's really a binary times 1 to n. So it's really pretty easy to work with. But so maybe as a homework assignment, derive derive these things that I put right here. You need some finite sum results for the sum of the integers from 1 to the n and sum of the integers squared, but other than that it's a pretty easy problem. But let's not waste time with that, because I don't see the true benefit of using the large sample approximation when you can use the small sample one anyway, unless there's ties or something like that. At any rate, the expected value of our statistic is n times n plus 1 over 4. Under the null hypothesis, the variance is this guy right here. And so our test statistic is just w plus minus its expected value divided by its standard error. That limits to a normal 0, 1. You can do a you can do the correction for ties if you want, but under the null hypothesis we can still do an exact small sample test, so why not just do that? Okay, so here let's go through our example. Here we take our differences. We can do Wilcox.test, diff, exact equals false, and then it's going to actually go through, I go through the calculations right here. It'll agree with the results of Wilcox.test. So I think now that I'm looking at this, I'm not sure, you may have to put correct equals false or something to make sure you're not correcting for ties. But anyway, double check to make sure that they're the same. They should be either exactly the same or very close, and the correction for ties is the distinction, which we don't really cover the little technical details like that in this class. At any rate, you get an expected value W plus is 150, the variance is 1,225, so our test statistic is our observed W plus 194.5 minus its expected value 150 divided by the standard error, works out to be 1.27. Of course, that's not significant on the z-scale, and so our p-value in fact works out to be 0.21. So what is this suggesting? This is suggesting that we can't rule out that the median is in fact 0. Okay, so that's the non-parametric equivalent to the paired test. Let's talk about the non-parametric equivalent to the unpaired test. And here we're comparing two measurement techniques, again from this wonderful book from Rice, Mathematical Statistics and Data Analysis. Anyway, they were comparing two measuring techniques, and the units are in degrees Celsius per gram. And here we have a group measured with method A and a group measured with method B. And we want to kind of test, are the measurements the same? And we'll be a little bit more formal about the hypothesis in a minute. But so let's talk about how we can do that. And so what basically the method we're going to use is, not to be confused with method A and method B, the technique we're going to use for testing whether the two methods are the same is to kind of take the A-B labels and shuffle them on every measurement. But because to be non-parametric, we're going to shuffle them on the ranks. But then we'll talk later on about shuffling them on the observed values themselves. That's the so-called permutation test. Okay, so what we're going to do is test whether or not the two measurements, two treatments have the same location. What I mean is kind of the distributions are centered at the same place. We're going to assume that the measurements are independent and identically distributed, have independent identically distributed errors that are not necessarily normal. So there's a difference between the errors being normally distributed versus the measurements being normally distributed. And that's one way to, so this is the problem with this test, is that's one way to write out the assumptions. Another way is to view this as a test of a kind of a distributional shift, that the distribution for method B is kind of uniformly shifted relative to that of distribution A. And that's called a stochastic shift for the two arbitrary distributions. So you can either kind of specify the hypothesis kind of tightly, that they're centered in the same location with IID errors, and then you get the same test statistic and it has a set of power for that particular collection of hypotheses, versus a very general one about a stochastic shift and it has a different kind of power for that set of hypotheses. So all we're going to use is we're going to disregard labels, method A and method B labels. We're going to rank the observations, and then we're going to use the sum of the ranks by discarding within each treatment label. And this is called the Wilcoxon rank sum test. It's equivalent to the so-called Mann-Whitney test as well. So, so you might call it, I don't know, the Wilcoxon Mann-Whitney test. In R, it's Wilcox.test. And I should say that there are some slight differences between the tests depending on how you the tests work out to be the same, but they characterize the test statistic in slightly different ways. But it's still, I think, correct to attribute the test to Wilcoxon and Mann-Whitney. Mann and Whitney being two researchers. So the procedure is to discard the treatment labels, method A, method B in this case, rank the observations without concern over which treatment they were, calculate the sum of the ranks in the first treatment, which is arbitrary. You could pick either the first treatment or the second treatment, you get the same value, but you have to pick one of the two. And then you either compare your statistic with the asymptotic normal distribution of the statistic, or you can calculate the exact distribution under the null hypothesis. So here I show the ranks for method A, the ranks for method B. In case the two observations are tied, we give them the average rank and then move on. The sum of the ranks for method A was 180, and the sum of the ranks for method B was 151. By the way, the sum has to add up to 231, by the way. And let's show, just because that's a fun result, let's show why this is the case. So Gauss supposedly did this as a child. There's some hypothesis that this story is apocryphal, but whatever. Let's, for our purposes, let's assume he did it when he was a kid. So as the story goes is that his teacher asked him to add up the numbers between 1 and 100, and he went down, sat at his desk, and just came back with the answer. And the teacher said, "That's not possible. How did you do that?" And then he went and really did it and got the same answer. At any rate, I think the story is probably apocryphal, but here it's really a neat way to show it. Is we could write x as the sum of the digits from 1 to n, 1 plus 2 plus 3, and in that way. Or we could write it as n plus n minus 1 plus n minus 2. It's the same exact thing all the way down to 1. So if you add the two together, you get 2x equals, and in this case, notice 1 plus n is n plus 1, 2 plus n minus 1 is n plus 1, 3 plus n minus 2 is n plus 1, and so on. And so 2x is n times n plus 1, which is exactly what's happening here, is the number n plus 1 added up n times, so it's n times n plus 1. So then x has to be n times n plus 1 over 2. Okay, so let's let W be the sum of the ranks for the first treatment. And then, you know, if a treatment has more numbers in it, then it's under the null hypothesis, it's going to have a higher sum just by virtue of having more numbers. So we need to know NA and NB, the number in each sample. And it turns out that the expected value of the sum of the ranks under the null hypothesis from the first group works out to be this guy, NA times NA plus NB plus 1 divided by 2, and so on, with a standard error given by this guy. And then we could create a test statistic, which is our W, our sum of our ranks in our first group, minus its expected value divided by its standard error. It turns out to be normal 0, 1. Of course, you can calculate the exact distribution as we described before. Okay. So let's go through our example. In this case, our sum of our ranks was 51. If we did method B, our sum of our ranks was 51. Here's our expected value and standard deviation of that statistic, 88 and 13. Our test statistic works out to be negative 2.68, p-value of 0.007 for two-sided. And then you can also do the function Wilcox.test, and it'll perform the test to you, both for the 1 and 2 sample version. You have to read over the documentation for Wilcox.test. If you give it 1 vector, it's going to do the sign rank test. If you give it 2 vectors, it's going to do the rank sum test. So some final notes about the non-parametric test is they tend to be more robust outliers than their parametric counterparts. They do not require normality assumptions. They often have exact small sample versions. And their big trick is to focus on the ranks rather than the raw data. There is some loss in power over their parametric counterparts, assuming the parametric assumptions are met, but the loss in power is often not so bad. And then I just want to emphasize, non-parametric tests are not assumption-free. They're often distribution-free. For example, the signed rank test, you really kind of have to assume that the distribution is symmetric. But either way, in all of the tests that we considered, you have to have a sampling model that the data is IID, right? That's an assumption, a big assumption, the biggest assumption. So it's, you know, so just to emphasize that non-parametric tests are not assumption-free. They're often distribution-free, but not assumption-free. And then, so I just wanted to remind people about permutation tests because we've already talked about them a little bit, sort of with regard to Fisher's exact test, but here we could also talk about them in general. So permutation tests are similar to these rank sum tests, though they use the data rather than the actual ranks. So under the null hypothesis for the rank sum test, we had the collection of ranks, and our null distribution was just obtained by permuting the treatment labels. You know, we had NA treatment A labels and NB treatment B labels, and we just permute those with respect to the ranks. That would retain NA labels and NB labels, but they would be randomly allocated among the ranks. A permutation test is exactly the same thing. You're just doing it to the raw data rather than the actual ranks, and you have to come up with the statistics. And I go through the procedure here. You know, you could permute the ranks and then create a rank statistic. I also want to, well, I want to distinguish, there's two ways to think about this. One is, imagine if your treatment was actually randomized, then you can think of the permutation test as actually kind of redoing the randomization. And in that case, the permutation test is called a randomization test if you interpret it that way. But you can also kind of perform the permutation test even if the treatment wasn't randomized, because you're thinking along the lines of, well, my null hypothesis is that my labels A and B are exchangeable between the groups. So either way, it kind of makes sense, but it changes your interpretation a little bit of the test in either way. But at any rate, the Fisher's exact test, the rank sum test, Fisher's exact test, which works on collections of binary data, the rank sum test, which works on ranking the observations, and then the permutation test, all have the same basic principle, is that under the null hypothesis, however we're interpreting it, is that treatment labels are, the NA and NB treatment labels are exchangeable, and our null distribution is obtained by permuting those labels across the values. In Fisher's exact test and the permutation test, we're permuting them across the actual observed values, and then in the rank sum test, we're converting the data to ranks first and then permuting across the ranks. So just to reiterate, this is an easy way to produce a null distribution for a test of equal distribution. It has kind of a similar flavor to the bootstrap, maybe not exactly. This produces an exact test. It's less robust but more powerful than rank sum test, because you're not throwing away the data. With rank sum test, you throw away the actual units and you go with ranks. So you gain robustness at the expense of power. This, you get a little bit more power under certain assumptions, but you lose some of that robustness. And it's very popular in large-scale big data applications like genomics, for example, and neuroimaging. So this final picture is just what you would aspire to get from a permutation test. You would permute method A and method B labels. You would say calculate the t-statistic as if the permuted labels were the observed labels, and you do that over and over again, and you get a null distribution of t-statistics, right? And then this vertical line is where our actual t-statistic occurred. And then if that's the case, then you, or whatever statistic, it doesn't have to be a t-statistic, but that's a reasonable statistic to do. And then the percentage of the simulated statistics that are more extreme than our observed statistic is our exact p-value. So that's a permutation test. If you were to do it with the ranks, then this would just be simulating the exact small sample distribution of the rank sum statistic. If you were to do it with the raw data, then it's a so-called permutation test, and so on.